So, in the last lecture you have seen we have started the Fourier series. In this lecture we will start with the convergence of Fourier series of a function, whether a function can be expressed in terms of Fourier series or not. If yes, under what condition a function can be expanded. So, let us see a theorem. Convergence of Fourier series. Any function f x can be developed as a Fourier series a0 by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n sin n x, where a n is a naught, a n and b n are constants whose values have been provided earlier, provided you see number 1 f x is periodic single valued function and finite. Please note this one, f x is a periodic function, it is single valued function and it is finite. F x number 2, f x has a finite number of discontinuities in one period. F x has finite number of discontinuities in one period. That means, the function may not be continuous throughout in the interval say 0 to pi, 0 to 2 pi like this, since it is a periodic function. But if I break it into n number of subintervals, in each of the subinterval the function has to be continuous. And number 3, f x has at most a finite number of maxima and minima. Please note this one, that a finite number of maxima and minima will be there. So, if a function f x satisfies these three conditions, then only we can expand the function f x in terms of a Fourier series, that is in terms of sine and cosine series, that the function has to be periodic, has to be single valued and the value will be finite. F x must have finite number of discontinuities in a cycle in a period, and it must have a finite number of maxima and minima. So, these are satisfied, then Fourier series of f x we say converges to f x at all points where f x is continuous. Also, the series converges to the average of the left limit and right limit of f x at each point where f x is discontinuous. So, from the first one I am saying, if f x is continuous at a point x equals x naught, then the series can be converges to f x equals f of x naught at x equals x naught. But if there is a point of discontinuity, say, in that case we are saying that the value of the series will be equals to average of the left hand side limit and the right hand side limit of f x at each of the points where the function is discontinuous. Suppose your function in the interval alpha to alpha plus 2 pi, we are defining something like this, f x equals some function of x, where x lies between alpha to c, and some other function of x where it lies alpha to alpha plus 2 pi. So, if you see here, c is the point of discontinuity in this case. At the point c, x equals c, it is a discontinuous, or in other sense, sometimes I may say that there may have a curve something like this, there may have a curve something like this. So, at this point, at some point x equals c or like that, at this point here at x equals 0, the function will not be continuous. So, it is the case of this one. In that case, what happens? Your a naught I have to write like this, 1 by pi into, I have to break it into two parts, function of x alpha to c some function plus c to alpha plus 2 pi some other function of x psi of x dx. Similarly, your a n also we can write down alpha to c phi x into cos n x dx plus c to alpha plus 2 pi phi x into, sorry, this will not be phi, but this will be psi x into cos n x dx, and your B n will be equals to 1 by pi alpha to c phi x into sin n x dx plus c 2 alpha plus 2 pi psi x into sin n x dx. If there is a point of discontinuity at the point x equals c, then a naught a n and b n can be evaluated like this: alpha to alpha plus c to alpha plus c. So, at x equals c, there is a finite jump in the graph of the function, or it is discontinuous. Now, here if you see at x equals c, if you try to find out the at x equals c, the left hand limit and the right hand limit at x equals c both exist, but they will be different. So, at such a point x equals c, the value of f x can be written as half into left hand limit, that is f of c minus 0 plus f of c plus 0. So, I think it is clear now that at the point x equals c, if you have a point of discontinuity, then the value of the Fourier series at the point x equals c can be evaluated as f x half into f of c minus 0 plus f of c plus 0, that is left hand limit of c and right hand limit of c. And please note that this is true whenever this is discontinuous, and if at x equals c f x is continuous, if f x is continuous, in that case the value will be f c. So, I hope it is clear. Whenever a function f x is given, we are finding the Fourier series, either the function f x will be continuous in the entire range alpha to alpha plus 2 pi, or there may have certain point of finite number of discontinuities. If it is continuous throughout, then at any point x equals c, value of the function will be f of c. If x equals c is a point of discontinuity, as I explained the example, in alpha to alpha c, it is a function of phi x, and c to alpha plus 2 pi some other function psi x, so that at x equals c the function is discontinuous. If the function is discontinuous, then the value of the Fourier series at x equals c will be half into f of c minus 0 plus f of c plus 0. Now, so these things we have told over here, whatever I have just now told, we are taking this particular function where a naught, a n and b n can be defined like this way. Once I have defined this, then at a finite discontinuity will be there at x equals 0, since there will be a jump, and in this case value of f x will be half of f of c minus 0 plus f of c plus 0. Sometimes we call this one as the Dirichlet's condition also. Please note that this we sometimes call as Dirichlet's condition also. Now, let us take an example. We want to find the Fourier series of a periodic function f with period 2 pi, that is, which is defined as f x equals 0 for minus pi to 0 and x for 0 to pi. So, basically your range is from minus pi to pi, and from there we want to find that, prove that the value of the series 1 plus 1 by 3 square, 1 by 5 square like this, this is equals to pi square by 8. So, to prove this one, your f x, what we have told, your f x is 0 whenever it is lying in between, and it is pi for 0 to pi. So, it is a periodic function with period 2 pi and the range is given from minus pi to pi. So, from the formula f x, as you know, you can write down f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus summation n equals 1 to infinity b n sin n x. What is our job? Our job is to find out the values of the coefficients a naught, a n and b n. To find the value of a naught, you know the formula, that is 1 by pi, limit here it will be from minus pi to pi f x dx. If you evaluate the limit, you will obtain this as pi by 2. Your a n will be equals to 1 by pi minus pi to pi f x into cos n x dx. Here your f x is equals to x. So, that I can write down 1 by pi 0 to pi, because minus pi to 0 it is 0. So, it is 0 to pi x cos n x dx, and if I evaluate it, 1 by pi n will come over here into cos n x by n from 0 to pi. If you put the limit of this, you will get 0 when n is even, minus 2 by pi n square when n is odd. So, therefore, your a n equals 0 if n is even, equals minus 2 by pi n square whenever n is odd. So, that from here I can find out a 1, a 2, a 3 like this way, a n. My next job is to find out the value of b n. B n again is 1 by pi, it is minus pi to pi f x into sin n x dx. Again this I can write down 1 by pi minus pi to 0, value of f x is 0. So, it is pi into x sin n x dx. If you evaluate this, you will obtain minus cos n pi by, this will be cos n pi by n. So, that it will be equals to minus 1 by n when n is even, and this will be equals to 1 by n whenever n is odd. So, please note that depending upon even or odd, sin n pi value, cos n pi value changes. Accordingly, we have to write down whether it is what is the value of b n a n whenever n is even or odd. So, we obtain the value of a naught, a n and b n. So, now you can write down the series f x equals a naught by 2. So, your a naught was pi by 2. So, it will be pi by 4 minus 2 by pi into, for b n a n it is 0 whenever n is even. So, that only odd terms will be there. So, that it will be cos x by 1 square plus cos 3 x by 3 square plus cos 5 x by 5 square, like this way it will go. Please note that here the since for n equals 0, a n is 0, for whenever n is even, n is 0. Therefore, even terms of cos will be vanishing, only the odd terms will be there. And similarly, here also you can obtain plus, this is alternatively it will go the sin, that is sin x by 1 minus sin 2 x by 2. The reason is when n is even it is minus 1 by n, and when it is odd it is 1 by n, plus sin 3 x by 3, like this way it will go. Now, what I have to find out? So, this is the first job of this one, that f x equals, what is the series that I obtained? I have to find out also now this value of this series, 1 by 1 plus 3 square plus 1 by 5 square, like this. this series. So, I have to check for which value of x I can obtain this kind of series. So, your sign terms will be 0 if I take x equals 0, and here only cos will be, since it is odd function. So, there will be 1 values will be 1 of cos n x. So, that from this series f x equals this, if I put x at x equals 0 on both sides, if I put at x equals 0, your f 0 is equals to pi by 4 minus 2 by pi into 1 by 1 square plus 1 by 3 square plus 1 by 5 square, like this way it will go. Sin terms will be vanishing and cos n x will be 1 at x equals 0. I can find out what is the value of f 0 also, if x is given to me. So, f 0 I can find out, and if I substitute the value of f 0, and I will obtain then 1 by 1 square plus 1 by 3 square plus 1 by 5 square, like this way. This will be nothing but 2 by pi is there. So, that it will be, if it goes on that side, pi square by 8. Please note that the function which was given at x equals 0, value of f 0 is 0. Please note this one, value of f 0 at x equals 0, it is 0. By substituting that, I am getting the value of this series 1 by 1 square plus 1 by 3 square plus 1 by 5 square equals pi square by 8. So, just let us see, as I told you, quickly let us see. A naught is this, because it is minus pi to pi. So, I have written, and this is equals, if I break it pi by 2, a n will be this, b n will be minus 1 by n when n is even, and plus 1 by n when n is odd. So, that I can write down the series once I know a naught, a n and b n values. So, once I am obtaining these values at x equals 0, f 0 will be equals to this value. Your sin terms will be vanishing, cos terms will be 1. So, that pi by 4 minus 2 by pi into 1 by 1 square plus 1 by 3 square, like that way it will go. So, that you can say that pi square by 8 equals 1 plus 1 by 3 square plus 1 by 5 square, like this way. So, in this way, whenever I have a function, I can express the function in terms of a sine series or cosine series, which we are saying as the Fourier series, and also from here we are finding the value of some finite series also. And now, let us see the next one, that is Fourier series for even and odd functions. What happens for the case of even and odd function? What is even function? As you know, your even function will be f of minus x equals to f x for all x. If a function f x satisfies this property, f of minus x equals f x for all x, we call it as the even function. So, that if you see f x cos n x always will be is even function, and your f x into sin n x, this is will be odd function. F x is even function, then f of minus x equals f x for all x. F x cos n x is even function, f x sin n x in that case will be odd function. What happens? Let us see what will be the effect on the calculation of a naught, a n and b n. Your a naught, a n is equals to how much? 1 by pi minus pi to pi f x into cos n x dx. Now, since f x into cos n x dx is an even function, therefore, from the formula, from the properties of definite integral, minus pi by pi, minus pi to pi can be converted into the 0 to pi. So, that I can write it as 2 by pi 0 to pi f x into cos n x dx, and your b n is 1 by pi minus pi to pi f x into sin n x dx. Since f x is odd function, even function, therefore, f x into sin n x is an odd function, and we know again properties of definite integral minus pi to pi, if the integrand is some odd function, value always will be 0. So, that you can say that the Fourier series of even function, if the function is even function, that consists of cosine terms only, there will be no sine term on this one. Similarly, whenever, so please note that your f x will be a 0 by 2 plus summation n equals 1 to infinity a n cos n x, when f x is even function. When f x is even function, then f x equals a naught by 2 plus summation n equals 1 to infinity a n cos n x, where a n is given by this, a n is equals to 2 by pi 0 to pi f x into cos n x dx. So, if I know the function is an odd function, I do not have to calculate b n. Please note this one. This is the reason we are doing the if it is even function and odd function, what will be the effect that we are trying to look from that angle. Now, suppose f x is odd function. If f x is odd function, we know it must satisfy this property, f of minus x equals minus f x for all x, f of minus x equals minus f x for all x. So, that f x into cos n x is odd function and f x into sin n x is even function. So, if the function is f x is odd, then f x into cos n x is an odd function and f x into sin n x will be an even function. So, that whenever I will try to calculate a n will be 1 by pi minus pi to pi f x cos n x dx, and since this is an odd function, therefore, value of the integral will be 0, and your b n equals 1 by pi minus pi to pi f x into sin n x dx. Again, f x into sin n x dx is an even function, since f x is odd function. So, that from the properties of definite integral, we can simply write it 2 by pi 0 to pi f x into sin n x dx. Therefore, if the function Fourier series of an odd function consists of sine terms only, not the odd terms, that is not the even cosine terms, but it will only consisting of the sine terms. So, in that case, I am calculating b n and a naught. So, let us just quickly see this thing. So, for the even function I am doing it, and a n is equals to 2 by pi 0 to pi f x cos n x dx. Similarly, b n equals 1 by pi minus pi to pi f x sin n x dx. This will be 0, since f x sin n x will be an odd function in this case, and the Fourier series will consist of cosine terms only. For the odd function, as you know, f of minus x equals minus f x for all x, then f x equals cos n x is an odd function and f x sin n x is an even function. So, that your a n equals 1 by pi minus pi to pi f x cos n x dx, where f x cos n x is an odd function. So, that the value of the a n will be 0 and b n is equals to 1 by pi minus pi to pi f x sin n x dx. f x sin n x is an even function, since f x is odd. So, I can write it 0 to pi f x sin n x dx. So, for even and odd function, we can calculate it like this. Quickly, let us take an Example, we want to find out the Fourier series for a periodic function mod x of period 2 pi. So, let us see, your function is f x equals mod x. So, the function f x, since it is mod x, so I can represent it in minus pi to pi like this, and it will be x into in 0 to pi. So, I am defining the function f x equals minus x whenever x lies between minus pi to 0 and x lies between 0 to this one. So, f x is an even function. Please note this one, f x satisfies the property of even function here. So, f x is an even function. So, at the beginning, if I know f x is an even function, then I know even function are expressed in terms of cosine series only. So, I have to calculate only a naught and a n. Your a naught will be equals to pi if you just calculate it, and your a n will be equals to 2 by pi 0 to pi x into cos n x dx. So, your evaluation becomes easier, 2 by pi n square into cos n pi minus 1, cos n pi is. So, this value will be changing depending upon the value of n. So, that this will be 0 whenever n is even, and this will be minus 1, cos n pi will be minus 1 whenever n is odd. So, that this in that case will become minus 4 by pi into n square when n is odd. So, these are the values of this, that a n a naught equals pi, a n equals 0 when n is even, and minus 4 by pi n square whenever n is odd. So, I can write down my f x as this one, f x equals pi by 2 minus 4 by pi into cos x by 1 square plus cos 3 x by 3 square plus cos of 5 x by 5 square, like that way it will continue. So, once I am writing this, your f x is represented like this way. So, please note that at the beginning itself, before finding the Fourier series of a function, if I check whether f x is even function or f x is odd function, in that case my calculation burden will be reducing, because if it is even function, it will have only the terms of cosine terms, or other sense you will have a naught and a n you have to calculate, whereas if the function is even function, in that case it will have the term sine terms only, that we will see in the next lecture.